We're now going to look at one of the other strange aspects about quantum mechanics, one that again distinguishes it from our classical view of the world. This is the idea of identical particles. Particles such as electrons can be identical to a level well beyond our ideas in the normal classical view of the world. We might think in the classical world that two objects, such as these two tennis balls, are pretty much identical. But we do believe that they are different objects, and if we examine them carefully enough, we'll find some differences in them. Those differences would allow us to distinguish one from the other in a way that would be reliable. We could always say that this is tennis ball A, for example, and this one is tennis ball B. But in quantum mechanics, particles such as electrons are apparently absolutely identical. There is apparently no way of saying which one is which. There is no reliable marker on the electrons that allows us to distinguish one from the other. This concept has a number of quite measurable consequences that are actually very important for how our world actually works. There is an analogy to the real world that is helpful here, but we'll postpone introducing that until we've looked more closely at this idea of identical particles. Suppose then that we have two electrons, and for the moment we'll presume that they can have the same spin. We'll imagine we can label one as electron 1 and the other as electron 2. As far as we know, however, there is absolutely no difference between one electron and another. They are absolutely interchangeable. We might think, because of something we know about the history of these electrons, that it's more likely that we're looking at electron 1 rather than electron 2. There is, however, apparently no way by making a measurement that we can actually know for sure which one we're looking at. This is reminiscent of the simple magician's action, where he might put something in each hand and then put both hands behind his back, and then bring them out again. You don't know if he's exchanged the two objects, but the difference here is that even if he shows them to you before and after, there's absolutely no way you can tell if he has exchanged them. You can't put a distinguishing mark of any kind on an electron. It's just an electron, and they're all identical. You might think the magician is not really likely to be able to swap them over behind his back because you don't think he's a very good magician, or he might not, in your opinion, have enough time to do this. Or you might think you'd be able to see his muscles move, though a smart magician will always wear a loose jacket with long sleeves. But with the electron, the idea is that there's no way of doing any measurement that will allow you to conclude for sure whether or not he has actually swapped them over. We imagine that the two electrons are traveling through space. So here we have a path A and a path B. And each, we presume, are in some kind of wave packet. The wave packets might each be quite localized in space at any given time, so perhaps one of them is localized round here, and the other is localized round there at some time. But these wave packets do extend sort of arbitrarily far sideways. We can never quite say where one stops, and similarly for the other one here. And the amplitudes might be quite small where they overlap, but the wave functions will always overlap to some degree in space here. Now, we may find the following argument more convincing if we imagine that the wave packets are, as on these paths, initially directed towards one another. So into some scattering region here, and that these wave packets substantially overlap in here for some period of time as they bounce off one another, possibly doing this or possibly doing that or something else. Now, certainly on the right of the scattering region, when we measure the electrons, possibly finding one near path A and another near path B, because the two electrons are absolutely identical, we have absolutely no way of knowing whether it is electron 1 or electron 2 that we find near any particular path. We might have good reason to believe, because our understanding of this scattering process in here, that if electron 1 started out on path A on the left, it is unlikely that electron 1 emerges on path B. But we have to accept that it could be possible, and we cannot distinguish whether that is what has happened just by measuring out here. So let's write the wave function psi A of r associated with path A, at least on the right of the scattering region out here. And this is for some particular time. And similarly, we'll write psi B of r for the corresponding wave function on path B. Hence, we might expect that the two-particle wave function, we put Tp in here for two-particle, which is a function of both the coordinates of particle 1 and particle 2, that it might be written on the right as some linear combination of the two possible outcomes. That is, particle 1 on path A and particle 2 on path B, with some constant out here, and particle 2 on path A and particle 1 on path B, with possibly some other constant here. And as I said, C12 is the amplitude for the outcome that electron 1 is on path A and electron 2 is on path B. And oppositely for this other amplitude, C21 here. But we believe electrons to be absolutely identical. So it can make no difference to any measurable outcome if we swap the electrons. We cannot measure the wave function itself, but we do expect to be able to measure the modulus squared of a wave function. Swapping the electrons would change this wave function, the two-particle wave function of electron 1 position and electron 2 position, into the other way round. We would have swapped around these position coordinates if we swapped the electrons. And so we conclude that if we do that swap, this modulus squared must be equal to that one, because we have no way of distinguishing one electron from another by measurement. So these two probability measures here must be equal to one another. Now, if these two probability measures are equal to one another, that means that this wave function with the 2 here and the 1 there must be equal to some number times the wave function with 1 here and 2 there, and that number has to be of unit magnitude. It could be some complex number that would be sufficient to give us this condition here, but it must be of unit magnitude. We could, of course, swap the particles again. Since the particles are absolutely identical, we expect this second swapping process produces exactly the same result. And so, again, we would now find that this two-particle wave function of R1 and R2 would be gamma times the two-particle wave function of R2 and R1. We're merely doing this swap again, and we presume it has to result in the same complex number here when we do that. With both of these equations then, which we're postulating, we conclude that this two-particle wave function must equal gamma squared times itself. That's what happens if we apply these two operations one after the other. We get back to the wave function we started with, but we've picked up gamma squared along the way. So, presuming, or postulating, if you like, that the wave function should be restored on this double swap, we're then forced to conclude that gamma squared is equal to 1. So we have only two possibilities then for gamma. Either gamma is 1 or gamma is minus 1. Hence, we either have that this two-particle wave function of R1 and R2 is the same with a plus sign as the two-particle wave function with R2 and R1, that is the particles swapped round, or it is minus the two-particle wave function with the particles swapped round. The minus corresponds to gamma equal to minus 1, the plus corresponds to gamma equal to 1. Now we can substitute our general linear combination that we postulated before into this two-particle wave function with this condition here. And what we're going to get, if we do that, is that on the left, here's our psi A of R1, psi B of R2, and psi A of R2 and psi B of R1, both the two parts of that, has to be equal to plus or minus the same thing, but with the particles swapped round. Now, I've changed the order of these two in the sum here. So here's C12 psi A of R2, psi B of R1, and C21 psi A of R1, psi B of R2. And I put the plus or minus out the front here. So if we rearrange this, taking all of the terms in psi A of R1, psi B of R2, then we get C12 times that minus or plus C21 times that. So that's taking this term, which is plus or minus C21 psi A of R1, psi B of R2, over to the left-hand side. Similarly, on the right-hand side, for the other term, psi A of R2, psi B of R1, we have plus or minus C12, and then we've taken this term over to the right-hand side, so we've got minus C21 times the same pair. So that's from here taken over to the other side. And we can rewrite this by a simple manipulation. We can just pull this out the front, and by putting a plus or minus in here, we can get C12 minus or plus C21. So when we have the plus sign here, we have the minus sign in here, and when we have the minus sign in here, we have the plus sign in there. But if we look at this expression here, we conclude, of course, since this must hold for every R1 here, and in general, psi A of some R1 is not equal to psi B of R1. This was the wave function on path A. This was the wave function on path B, because these are largely different wave packets that are rather separate in space. Then the only way this can work is if this term here, which appears on both sides, is 0. So the only way this equation can work in general is if this term, which appears on both sides, is 0. So in this expression here that we had for our postulated two-particle wave function, we must have that C12 is either plus C21 or C12 is minus C21. Those are the two possibilities that allow this term to be 0. If this notation looks a little confusing, what we're saying is that if we chose gamma equal to plus 1, then we would have to conclude that C12 is equal to C21, and if we chose gamma equal to minus 1, then we'd have to conclude that C12 is equal to minus C21. That's what this notation is really telling us here. So, given that the electrons emerge on these paths A and B, we presume, we've shown that there are only two possibilities for the nature of the wave function on the right of the scattering volume. Either, with gamma equal to plus 1, this two-particle wave function is some constant times psi A of R1 times psi B of R2 plus psi A of R2 times psi B of R1. Or the same expression but with a minus sign in here. And C at the moment is in general some complex constant. We have therefore proved that on the right, the amplitudes of this function, which is particle 1 on path A and particle 2 on path B, and this function, which is particle 2 on path A and particle 1 on path B, are equal in magnitude, though possibly opposite in sign. But we might say, for the electron on path A on the left, the scattering probability into path A on the right is in general different from the scattering probability into path B on the right. How, therefore, can we have the amplitude of the two possibilities on the right, that is, particle 1 on path A and particle 2 on path B, and the opposite, particle 2 on path A and particle 1 on path B, be equal in magnitude? The resolution of this apparent problem is that even on the left of the scattering volume, at some time before the scattering, the wave function, two-particle wave function of R1 and R2, must also have had the two possibilities, particle 1 on path A on the left, which I've called A before here, and particle 2 on path B on the left, which I've called B before, and similarly, particle 2 on path A before and particle 1 on path B before, must also have been equal in magnitude. These two possibilities must have been equal in magnitude before we started. Specifically then, even before the interaction, the wave function must either have been of this form or of this form. These are the wave packets to the left on each of the paths here, and we can have either a plus or a minus here. If we presume this, we get no contradiction anymore. It's quite possible for electron 1 to appear on path A or electron 2 to appear on path A with equal probabilities.